I hope you can hear me.
Yes, sir.
Sorry about the interruptions. I'm getting disconnected sometimes, maybe because of rain. Anyway, we'll move on. Right. This is an example. So take a piece of paper, draw these two coordinate frames, the red one and the blue one, right? And I want you to get me the 3x3 matrix, ABR. Very straightforward question, right? ABR, what is the orientation matrix of B with respect to A? I can assist you a little bit. This is the ABR format. Okay. If you want to write the first column, you first figure out the unit vector along x-axis of frame B. The unit vector along x-axis of frame B. And then find out the dot product or the shadows it creates on A, B, and C, right? A, X, Y, and Z axis of frame A. That's all what you need to do. You understand the point? First, figure out the unit vector along x-axis of frame B, x hat B, right? And then calculate the shadows that creates on the three major axes, X, Y, Z, of frame A. And repeat the pattern for Y hat B, Z hat B. That's all what you need to do. Take a minute and do that. So let me ask you, some of you guys, about your answers. Right. Vikramathilaka, have you got your answers? Vikramathilaka, are you there?
Sir, I haven't finished it.
Okay, take your time. Viketaran, have you been able to compute ABR? No? Sendanayaka?
Not yet, sir.
Okay. Rumesh? No? Rumesh, are you there? Ranasingha?
Still doing it, sir.
Okay. Shamal?
So still doing, sir.
Shifla?
Still doing, sir.
Okay. Jairatna?
I have done, sir. 1, 0, 0.
First column.
Yes. First row, sir.
What is the first column?
1, 0, 0.
First column is 1, 0, 0, right? Second column?
0, 0, 1.
0, 0, 1. Third column?
0, minus 1, 0.
0, minus 1, 0. Right? We have one answer. So that is Arya Tilak, right?
Jayarath.
What's your name?
Jayarath.
Jayaratna.
Yes, sir.
Any other answers? Okay, so let me show it to you. Now, the first thing, if I pedal back, you will see this is the technique, right? First, figure out x hat b, and then calculate the shadow that creates on major three axes, x, y, z of frame A. So that is the technique. So get x hat b. X hat b is this, right? Unit vector along this line, 1 unit long, right? And the shadow it creates on x hat A, the blue one, right, is 1. And the shadow it creates on y hat A, this blue one, is 0 because this is 90 degrees, no shadow there. And the shadow it creates on z hat A, the vertical one, is also 0. So therefore, the three shadows it creates on x hat A, y hat A, and z hat A are 1, 1, 0, 0. So Jayaratna has got it right, 1, 0, 0. Now you move on to the second vector, that is y hat b, right? Y hat b. So y hat b is along this line, right? 1 unit long. So you have to calculate the shadow it creates on x hat A, y hat A, and z hat A. So again, because of the 90-degree thing, there's no shadow on x hat A, there's no shadow on y hat A, but there is a shadow on z hat A, and that shadow is 1 unit long. So therefore, the second column of the rotation matrix is 0, 0, 1. So Jayaratna has got that correct too. Then comes the third one, that is Z hat B. This is the Z hat B axis along this line. Okay, along this line, 1 unit. The shadow it creates on x hat A is 0. Shadow it creates on y hat A is -1. It is on the line but opposite direction. So therefore we call it -1. And then z hat A, there's nothing. Okay, so it is 0, -1, 0. 0, -1, 0. So Jayaratna's answer is correct. So Jayaratna, I'll give you 2 points, right? I'll mark it and I'll give you 2 points and add it to the final score at the end of the semester, right? So good job.
Thank you, sir.
All right. So I don't want to explain it again. I explain the complete answer to you, right? It's not a difficult thing, but I think fundamentals are extremely important. Okay. Now, with the rotation matrix, you can transform coordinates from one frame to the other. So I'll give you one example. For example, say there is a vector attached to the frame here like this. Okay, so it is coordinate frame B, right? And the vector is, let's say, 2, 3, -1, something like that. 2, 3, -1. Okay. Now you want to get this point written with respect to frame A. So all what you need to do is the vector with respect to A is equal to the matrix, this one you have just calculated, and then multiply by this vector 2, right, 3 and -1. Okay, simple as that. And if you want to do the other way around, matrix inverse, right? So you have a vector attached to frame A and you want to find it with respect to B. Then what you do is you write the same matrix, and now you get the transpose, and you have the new vector, the second one, and now it is B, P, the vector with respect to frame B. Okay, so here what you write is A, P. Sorry about that, but if you understand. So if you want to transfer coordinates or change the description of a vector, right, from B to A, you do this way. From A to B, you do that way. You use the same rotation matrix, but when you change the direction, you use the transpose. Right. You use the transpose because in orthonormal coordinate frames, the rotation matrix, right, is inverse is equal to transpose. We have seen that. So now I'm going to give you this little exercise as a homework. So the rotation matrices we have computed, we studied using the cross product, dot product between the two major axes at a time, right? And you know this dot product comes from the cosines, right? Therefore, you can look at the angle, the rotation between two frames. If I ask you to figure out what sort of rotation is this, right? What sort of rotation is this? You can see the reference frame is blue, right? The relative frame is red. It looks to me, because x axes are aligned, this is a simple rotation. This is a simple rotation of frame B, right, around x-axis of frame A, around x-axis of frame A, right, by 90 degrees. So you can see it over here, right? This rotation is 90 degrees around x-axis of frame A. Okay, so after this rotation, 90 degrees around x hat A, you have this new position of red frame. So how do you relate this rotation 90 degrees around x-axis to this 0-1 combination? 0-1 combination. If you want to find that out, this 90 degree is not good. You put another arbitrary angle, theta. Okay. So here what you see is 90 degree rotation. But if you have a smaller angle, you will see it better, right? Say this is the original position, right? And then you rotate small angle like that. Okay, this is the second axis. So this angle is theta. So as a homework, please do this, right? You rotate one of the coordinate frames by angle theta around x-axis and get me the rotation matrix. Now you can do this rotation around y-axis, around z-axis. So every time you do the rotation, make sure this axis is the axis of rotation. It can be x initially, but when you do it for y, change it to y, then to z, right? Axis of rotation has to be this direction always. Then you can actually calculate the rotation matrix. All right. Now we have given the label for this rotation as ABR, but in fact, to be precise, this is ABR. Yes, correct, right? But more correct representation is that it is a rotation matrix. Let's call it ROT, rotation matrix. Then within bracket, you can say around x-axis, right? 90 degrees, like that, right? So this is the this is the rotation matrix for a rotation around x-axis by 90 degrees, right? So else you can say R X within bracket 90. Okay, something like that. So what I'm asking you to do at homework, as a homework, is that, so get me this one, Rx theta, Rx theta, the rotation matrix for a rotation around x-axis by an angle theta. And then get me rotation about y-axis, right? About y-axis by an angle beta, rotation about z-axis by an angle gamma, alpha, beta, gamma. So you derive it yourself, draw 3 diagrams, right? First one, like this, x-axis out of the board, and then y and z are there, and find out the rotation matrix, and then draw another diagram, this time y-axis out of the board, and do the computation, calculate the rotation matrix, and then third one, draw another frame with z-axis out of the board and calculate the rotation matrix. Then you will see what is called the basic rotation matrices. The basic rotation matrices for a rotation around x-axis by an angle alpha, for a rotation around y-axis angle beta, for rotation around z-axis angle gamma. Okay, these are the basic 3 rotations. Please do this as a homework. Next time I'll check that out. Now, if you want,
Excuse me, sir.
yes.
So could you please repeat that how it will be around y and z rotation direction?
Yeah, if you can do it for x-axis, why can't you do it the same thing around y and z-axis? There's no change.
Is that y-axis the direction of rotation? Like is
Yes,
that
axis of rotation, axis of rotation. So here what we have done is a rotation around the axis, x-axis.
Yes.
Axis of rotation here is x. So I want you to do it for a rotation around y-axis and around z-axis. Okay.
That clockwise, anti-clockwise difference?
Usually when we say is anti-clockwise,
Okay.
a positive rotation.
Okay, sir.
Okay, so here you can see the rotation is around x-axis. So when you have the axis of rotation, you rotate y to z. Understand? Y to z. So that is the positive direction. So remember that. So we should be consistent with all the coordinate frame rules. This is a right-hand coordinate frame. So if you rotate anything around x-axis, the rotation has to be positive rotation. Y-axis goes towards z-axis. Okay. Yeah. So when you do it for the y, same thing. Z has to go to x. Right. And if you rotate from around z-axis, x has to go to y, like that. Okay. Right. All right. Thank you for that question. I think it'll help others also, right, who might have the same concerns. Right. Then comes the frame description. Description of a frame, that is a complete description of a coordinate frame with respect to a world coordinate frame, right? A base frame. So here you can see the blue frame is the reference, and there's another frame in space, frame B, and it has a certain, it is disoriented with respect to A, and now you know how to describe the orientation, and also it is translated, linearly shifted to some other point. So complete description means you need to account for the two motions. One is the linear motion, that is the linear shift of the origin from origin of A, and then the second thing is the rotation. So this is how you put them together, right? You have ABR, that is the rotation part, and then on the side you have the APBORG. APBORG is the position of the origin of B, or relative frame, with respect to the reference frame. So when you do that, right, you know this is 3 by 3. This is 3 by 3 matrix. And APBORG is a vector, right? Is a 3 by 1, 3 rows and 1 column, 3 by 1, right? So it will look like this. So this is the rotation matrix part, right? It is 3 by 3, like that. And then over here you have the direction, the translation part, right? APBORG. So this part is now 3 rows and 4 columns. 3 rows and 4 columns. It's not a square matrix, which can cause problems in computation. So therefore, what we do is we put another row over here, right? With 0 here, 0 here, 0 here, and 1 here. So this becomes 4 by 4 square matrix. Okay, 4 by 4, which is a square matrix. So that we like to have square matrices. And the last row is redundant. We don't use it. Here we have the rotation part. This is the translation part. Okay. So that is the complete description of a relative frame with respect to a reference frame. So you can see in this illustration, a vector belongs to frame B, right? That is BP, right? And frame B is translated like this, APBORG. And if you go to the endpoint over here, right? If you want to write that point with respect to A, this is AP, right? AP. Now you can see 3 vectors here, AP, BP, APBORG. And it's a vector triangle. You have seen vector triangles, right? Vector addition and all. So I want you to tell me how I can calculate AP. Any answers? What is the answer for AP? If you know APBORG, that is this one. If you know this vector, and if you know this vector, how can you calculate this vector? Let's say this is the Earth. This is the Earth. Let's say this is the moon. Okay. And let's say this BP, this point is a lunar spacecraft which is going around the moon. Okay. So this is a spacecraft, right, around the moon. And then those who are on the moon can see the spacecraft, right, along this vector. All right. And moon is far away from the Earth, and it is defined by APBORG, basically the distance. And now if I ask you, okay, what is the description of the spacecraft with respect to the Earth? So I'm relating to something physical, right? For you to understand that the problem you are dealing with is very much physical problem, right? Different worlds, different coordinate frames, but you want to describe position and orientation of an object, right, which is defined with respect to a certain frame. Now we want to change the description with respect to another frame, right? So in this very simple example, what is the answer for this one, AP? Anybody can answer?
AP plus BP.
Say it again.
APB plus BP.
So I'm going to write it A P BORG, right?
Yes, sir.
Plus sorry about my writing. I don't have a touch screen here. Plus BP. Right. So this is what you have learned, right? Vector triangle. If you add two vectors in a triangle, the result is the third one, and you have to follow the directions, right? Fine. Is it correct here?
Sir, BP should be rotated, right?
BP should be rotated. Can you?
Sorry,
can
that
you-
means,
Yeah.
sorry, that A rotation B into BP. That should be added with
Okay.
the PBOR.
Excellent, excellent. So, but can you explain mathematically why this is not correct? What you see on the board?
Frame B is rotated already, and the origin also shifted. If the rotation is not done, only origin shift, then other answer is okay.
I know you understand the problem, but why it is not correct? If your answer is not perfect. Your answer is not perfect, but you have the point here, right? You can't add these two vectors like this.
Because they are not in the same coordinate system.
That is the point. That is the point. You cannot add dollars to rupees. Fundamentally, right? You can't add two vectors that belong to the two different coordinate frames. No, you can't add. You can add vectors, right? As long as they belong to the same coordinate frame. Because the vector triangle that you have been taught all this long, right, was always with respect to single frame. So therefore, you kept adding all these vectors, right? Because you had only one frame. It's only now you have multiple frames and different vectors belong to different coordinate frames. So you can't simply add them together because some of these coordinate frames are disoriented, right? So you can't simply add them together because x and x are not aligned, right? So before you add two vectors in a multiple coordinate frame system, you got to transform all these vectors into one single frame. After that only you can add. So the question asked here is AP. So AP means the reference is already set. The reference frame is A. So you have no choice than transforming all the vectors to frame A, right? The coordinate transformation, what we have learned, right, before the break will come in handy. You have to use that and figure out the rotation matrices required and transform all the vectors that are not belonging to frame A to frame A. Okay. So here we have two vectors, APBORG, right? APBORG and BP. So if you look at these two vectors, APBORG is a reference to A anyway. So therefore, there's no problem with that vector. But BP belongs to B, a different coordinate frame. That is the problem. So before you can add, you have to write it with respect to A. So can you tell me, how should I write it then? What should I do? What should I write over here?
The rotation matrix.
Yeah, so tell it to me. What is it?
ABR.
ABR, that's right. So I write it like this, ABR. So ABR, BP. So when you do that, this vector will be described, same vector, but it will be described with respect to A. After that, you can add them together. Excellent. So please tell me your name. I want to give you 1 point for that answer. What's your name?
Jayaratna.
Jayaratna, same Jayaratna. So you scored 3 points today. And the lady, tell me your name. You also will get 1 point.
Shifla.
Shifla.
Yes.
Wait. Shifla, you picked the point, but you are not able to describe it mathematically. And Jayaratna did it, but I'll give you both of you 1 point each. Thank you. This is really interesting. It's okay not to know things, but it's not okay not to interact, right? When you interact only, you will learn, right? So I appreciate those interactions. It's much better today. Okay, so we move on. Now we have put things together. If you look at the equation right-hand side, you can see the developing situation. APBORG already referred to A, and BP is transformed or redescribed with respect to A, and now you can add them together, right? So then this is the result you get, and I explained you, remember, few slides back, this one over here, right? 3 by 3 rotation matrix and 3 by 1 position vector. Doesn't look really good because it's not symmetric. Then we have these padding zeros and 1 perspective transformation. That's how we call it in computer science to make it a 4 by 4, right? Excellent. So in order to make the two sides equal, on the left hand side, which was like AP here has only 3 coordinates, but now it's a 4 by 4. You want to add this 1 over here, and also on the right hand side you add 1. This 1 and 1 is basically to make this mathematics into what is called the linear algebra platform, right? So they are not really useful, but we can't continue this linear algebra description without them. So that's why they are there, right? So now if you look at this matrix, it's like weird, right? The left top 3 by 3 and then the left right top 3 by 1. You can make that into one single matrix called ABT. So ABT is we call it homogeneous transformation matrix. It has both rotation and translation information together in a 4 by 4 matrix, right? 4 by 4 matrix. Right. Now let's look at the inverse transform, because every transform we need to study the inverse also, because we might need to change the reference to relative and relative to reference, right? So when we do that, if the transformation is not only rotation but translation together, right? Now we have the homogeneous transformation matrix, not just the rotation matrix. How we go about it? You remember the rotation one, when you do the inverse, it was very easy, right? Eventually it was like the transpose, right? But when it comes to rotation and orientation together, it is not that easy. But always you need to look at the physical manifestation of what you are doing mathematically, right? Wherever possible. So here we have the blue frame again and the red frame, blue and red frame. Blue is the reference, red is the relative. And you can see PAORG, that is origin A, and PBORG, that is origin B. Okay, so it's the same vector but two different directions. So when you look at B from A, it is this red vector over here, PBORG. So when you see from B, right, when you see A from B, then you are referring to this PAORG. The translation is different. And these vectors are not simply negative. You can't just have one vector and put a minus sign and say it is equal to this one. No, it's not going to be correct, because the directions because the orientation. Okay, I think you understand the point. Now what we want to calculate is this. Given ABT, so ABT means you have ABR and then APBORG and 0001. So this is given to you. What we want to calculate or determine is the opposite of this, the inverse of this rather, that is BAT. BAT, in other words, is ABT inverse, okay, inverse matrix. Can we determine this from ABT? From ABT, this one. If at all possible, it's easier, right? Without deriving it all over again. It's so much easier if you can reuse whatever you know, that is ABT information, and then adjust it, right? Modify it so that it becomes BAT. So that's what we want to do. So let me walk you through this illustration, because it's a bit difficult otherwise. Now here we have the reference frame A and the relative frame B. Very easy to understand. A, P, B, O, R, G is the vector. All right. So the inverse uh, um, inverse homogeneous transform matrix that you need to develop is BAT. BAT. So when you say BAT, if you follow the procedure here, right, there's a pattern, right? For any reference frame, for any relative frame, you know how to write this one, right? So this is the reference frame. This is the reference frame. This is the relative frame. This is the relative frame. This is the reference. This is the relative. They have specific positions in the structure. Reference doesn't have to be A all the time. Reference can change, but whenever it changes, you change it in the structure. All right. So I'm writing BAT. BAT. So when you say BAT, B is the reference. So I have to write B over here, B over here, right? And then A is the relative frame. So I have to write A here and A here. Simple as that. Okay, once you learn it, you just have to repeat it. So you should be able to write homogeneous transformation matrix of any two frames, X, Y. Okay. PQ or whatever, two frames. Figure out what is the reference frame, what is the relative frame, and then put that into the structure. Right. So we want to find out this one. Now look at the right hand side where you have BAR. Do you know BAR? I think you know it. BAR is the inverse of ABR. Is the inverse of ABR. But we don't like inverse. Instead, we can use the transpose. So this part is okay. This is the transpose of ABR. And AB is known. These are known. These are known. ABR is known. ABB or ORG is known. These two quantities are known. So when you get this one and get the transpose, it is equal to this one, BAR. So therefore, that part is already done. Now the problem is this one, BPAORG. How can we get an expression for this one? Let's see. So I modified the illustration a little bit. There you can see I have changed the reference to B now. Here in the first illustration, reference is A. Here, the second one, reference is B. Okay. So when I have reference frame changed, every vector has to undergo this pre-multiplication by the rotation matrix. You picked it up earlier. Jayaratna picked it up earlier. Whenever the reference frame changes, you have to pre-multiply the vectors with the rotation matrix. Okay, in order to change the vector description. So therefore, this vector APBORG, which belongs to A, which means the reference is A. Now, when the reference changes to B, right, you can't just say APBORG, but in front of that, you need to write BAR. So BAR is the rotation matrix of A with respect to B. Okay. It's very simple. You change the frame of reference, you pre-multiply the vector with the rotation matrix. You have to keep an eye on what is the reference frame, what is the relative frame. Don't mix things up. So this is the vector of origin of frame B, right? With respect to A, it's here. With respect to B, it's like this. Okay. Now, What you want is not origin of frame B, but the origin of frame A over here. Now this is the reference frame. This is the same vector. As long as you don't change the reference frame, if you want to change the direction of the vector, you just put the minus sign. You just put the minus sign in front of that. Then this vector change the direction and it will look like this. And BAR is unknown, right? But ABR is known. So therefore, what we do is we replace BAR with ABR transpose. Sorry about this again. This has to be ABR transpose. I will make that the correction. Times APBOR with a negative sign. So up here, we have changed the reference frame to B, and also we have corrected the direction. We have reversed the direction of the arrow. So this is the vector of origin of frame A with respect to frame B. So it has changed the rotation correction as well as the direction, heading correction. All right. Now this is equal to BPAOR. So you replace this one with this one and replace BAR with ABR transpose. This one transpose. Okay. So when you put these things together, this is correct, right? BAR change to ABR transpose. BPAORG changes to ABR transpose APBORG. So this is the inverse homogeneous transformation using the forward homogeneous transformation matrix and its component, right? So please take down this one, right? You can get a photo of the screen and work this out. So there you have two coordinate frames A and B. Determine the homogeneous transformation matrix ABT and vector AP. Determine the inverse homogeneous transformation matrix BAT, right? So I want you to do that and submit me online. I will put this as a quiz for this week. Please do it and submit before the next class, right? It's a simple thing. And I will upload the lecture and the slides tomorrow or Monday. You can download the lecture slides up to the whole slide set. It will take another couple of weeks to finish it up, but anyway, I will put everything online. And make sure you submit your answers to the Moodle within the week, right? Before I start the next class. And also the homework I gave you, right? You don't have to submit me that, but keep it with you, right? The basic homogeneous basic rotation matrices, right? Around the three major axes. I think it's extremely important that you actually do yourself, right? All these exercises without copying from others. You do it yourself. It's not that hard. You can do that. That is extremely important. Fundamental skills, right? As I always say, if you know what is happening physically, it is easier to understand the mathematical descriptions, right? But if you do not know physically what is happening, it will be very, very stressful just to follow mathematics. And you should not go down that path. All right. Any questions before we wind up today? Right. So if there are no questions, we will wind up for today, and I'll see you next week.
Thank you, sir. Good night.
Thank you, sir. Good night.
Thank you
you.
and good night.
Thank you, Mr.
All right. So this is the example we started working out last week, right? So there you can see two coordinate frames, blue and red. We are going to find out their relationship and then try to find out how we can describe a certain point that belongs to a certain coordinate frame and with respect to the other frame, right? So both these coordinate frames are three-dimensional coordinate frames. However, if you have noticed it, you can see this YZ two axes, Y and Z here, okay? And Y and Z here, okay? They are on the same plane. They are on the same plane. That is the first thing you are supposed to notice, okay? You are supposed to notice that both these axes, Y and Z, of the two frames are on the same plane. So how do you know that? If you look at this point, if you look at this point, right, which is the origin of frame B, what are the coordinates of this point? 0, 3, 1, 0, 3, 1. And the x coordinate is 0. X coordinate is 0. Right? And then you can see this point here, right, with respect to frame B, and the coordinates here are 0, 1, 1. Again, Z coordinate is 0. All right. So this point and this point are on the same plane. Z coordinate is 0. So therefore, it is both these points are on YZ plane because the Z coordinates are 0. And what about this point? Anyway, right, with this coordinate is with respect to this one. So x coordinate 0 here. Obviously, you can see it, right? So therefore, these 3 points are on the same plane. So let us assume this plane is the plane of the computer screen, okay, this white screen. So therefore, you can actually measure and find out the distances. This is not in actually three-dimensional space. This triangle is on the plane that you see, right? So now you are asked to find out this point, which is 0, 1, 1 with respect to B, right? With respect to A. So the point that you read as 0, 1, 1 with respect to B, how do you read it with respect to A? So that is the question. Okay. The first thing, determine the homogeneous transformation matrix, ABT, and vector AP. So this is how the question is asked, right? So you are supposed to find out the homogeneous transformation matrix first of B with respect to A, right? So then you need to find out what is this rotation. If you can see this x-axis like parallel to each other, right? And then y-axis like aligned with z-axis here, and z-axis aligned with negative y-axis here. So this is the same rotation we worked out last week, right? It's a rotation around x-axis of A, right, with respect to A. This is the reference frame. Let's say this is the relative frame. So the relative frame, that is B, has undergone a rotation 90 degrees around x-axis. Okay. So you can use the same homogeneous transformation matrix you derived last week. And then if you want to calculate AP, right, what do? You have this axis plus this vector, but this one you cannot add straight away. You have to pre-multiply it with the rotation matrix and then add. But if you get the homogeneous transformation matrix, you don't have to do these two together, two processes. You can do it in one process. Homogeneous transformation matrix is a is a 4x4 matrix. You know that, like this, 4x4, right? And this is the rotation part. This is the rotation part. That is A to B with respect to A rotation, right? You have to get that one. And this is actually 0, 3, 1. This is the origin of frame B, right, with respect to A. And this is 0, 0, 0. And this is 1. So if you work like this, right, it's so easy, then you can say, okay, you have BP here, right? Vector belongs to B, and the result is AP, right? So easy. So that's how it works. After that, the second part is determine the inverse homogeneous transformation matrix, right? So for that also we have the standard equation. Remember, this one you can use inverse homogeneous transformation matrix once you know the forward transformation and also the origin of the second frame. You can put that into this frame and get the inverse homogeneous transformation matrix. So when you do that, this is what you get. ABT homogeneous transformation matrix is this one, right? So you can say 0, 3, 1, which is the origin of the frame here, this vector actually, right? With respect to frame B, sorry, frame A. So you just write 0, 3, 1. And this is the rotation matrix. Remember last week, I think Ari Tilaka figured it out, the rotation matrix of B with respect to A. And these are padding zeros, and this is the perspective transformation element, which is 1. Then BP is this one with respect to B, 0, 1, 1, 0, 1, 1. But you have to add another 1 here, right, to match it with the dimension. So after that, you use this equation. AP is equal to ABT times BP, and this is the answer, 0, 2, 2. Now, the interesting thing is this. Just because you got some answer here after going through mathematical process, you should not wipe your hands, okay, and say, okay, I'm done. Most of the engineers, at least the students we work with, they're like that. Once they get the answer, they think it's over, right? Most of the time they don't take this additional minute or two to verify whether you have got is correct. I think that is extremely important, right? Like when you go shopping, right? You purchase things, right? You check and you buy, put it in your cart. And also if you order something online, first thing you do is that what you get is what you ordered, right? So this is a very generic practice everywhere, right? If you go to a market and if you pay something, you check the balance, right? Whether it is right or not. So like in every design, you have to do that verification. Every mathematical solution, you have to check whether this makes sense, okay? Sometimes a simple mistake can finally make your final answer. Everything was correct up to about 90, 95%, and last step, there's a silly mistake, right? And the answer is not correct. If you don't check, you would probably miss to figure out that silly mistake. So here, you have an answer, 0, 2, 2. So how do I check whether this is right or not? Can somebody tell me whether the answer I got is right or not? Any answer? Now, if you don't have any verification, you don't have the complete assurance that what we are doing is right. Okay. You are not confident. You are not fully confident of what you are doing is right. Like homogeneous transformation matrix, coordinate transformation, the theory I learned, I taught you, I explained to you, right? You are not 100% sure about it because you haven't seen any hard proof. Okay. So this is the hard proof here. Now the answer we have got is 0 to 2. That is the point here, this point, right, with respect to coordinate frame A is 0 to 2. Now let's check it, whether this is actually 0 to 2. So just a while ago, right, I explained and you understand that this triangle is on the plane, on the screen that you see, right? And this point is 0, 3, 1. 0 is the x coordinate because there's nothing coming out of the board, nothing going into the board, right? It's on the plane of the board. And y coordinate is 3, which means along this y direction, it is 3 units, 1, 2, 3. And along z direction, this is it, 1 unit, this is 1 unit, right? So if I just draw it to you, right, it's like this. From here to here, the length is 3. And from here to here, the length is actually 1. So that is the scale. So now this is a scale drawing. This is a scale drawing, right? So and this point is 0, 1, 1, which means this is with respect to B. So y coordinate here is the vertical coordinate. It is 1. So therefore, this distance is also 1. So with respect to A, right, this point stays on the plane, that is x is 0. So therefore this is correct, right? X is 0 is correct. So we can say, okay, this is fine. And then with respect to other coordinate axis, right? Let's say, for example, the length along y direction from here to somewhere here, right? Here to somewhere here. So the total length is 3 from here to here. So this is probably 2, right? Because you know, now z direction is also 1 here. I can draw it like this. This distance is from here to here. This is also 1, right? Because this is the z direction of B, right? Z direction. So it is 1. So therefore, if you look at from A, from here to here, the distance along y is 2 units. Okay, 2 units. So this is also correct. This is also correct. Then comes the z coordinate, right? Height from here, right? From here upwards, right, to this point. So obviously 1 and 1 is 2. So therefore that is also correct. This one is also correct. So this is a complete proof as to what we have been doing. The theoretical development that we have done is actually correct, right? This is a very easy mathematical tool to describe a vector which is attached to one frame right? And write it with respect to another frame. Okay. All what you need to know is the homogeneous transformation matrix. All right. So the homogeneous transformation matrix has the rotation part as well as the translation part, right? So the rotation part and the translation part. All right. Any questions so far? All right. Then let's move on. The second thing I ask you to do as a homework is the basic rotation matrices. So what you have seen here, right, is also a rotation, basic rotation, and it is around what? It's around x-axis. It's around x-axis, right? Angle is 90 degrees. Around x-axis, angle is 90 degrees, and this is the homogeneous. This is the rotation matrix. So if the rotation is around y-axis, z-axis, and a non-90 angle, any angle, plus or minus, right? You should be able to tell me for any angle, say alpha, or beta, gamma, right? What is the format, structure for rotation matrix? Have you done it? Has any one of you done it? Let me ask Shifla, have you tried it? The basic rotation matrix around X, Y, and Z? Palavatta, have you tried? Ranasinghe? Are you there? Vigitaran? By the way, are you guys there?
Yes, sir.
Yeah. So please answer. Yeah.
Yeah, I got disconnected several times. Actually, I couldn't work on during last week due to personal matters, sir.
Right. Who is this, Shifla?
Yes, sir.
Okay. Palavatta, Ranasinghe, Sendanayaka, Vigitaran, Vakasinghe, and Vikramatilaka.
Sir, excuse me.
Yes.
Sir, I went to that this rotational matrix one, but that other one I couldn't do. Sir.
Right. So hasn't anybody done it? Like all of you? Like we have probably 8 people, 7 people here. All 7. So none of you guys have. Tell me who has tried, please, but couldn't get the answer.
Hello.
Yeah.
So I tried, but I don't know whether the answer is correct.
That's okay. Just tell me, what did you do? What was the rotation you tried? Around which axis and what is the angle?
Around x-axis by an angle of alpha.
Alpha,
So
right.
I got the matrix 1, 0, 0.
Okay.
0 cos alpha minus sin alpha.
Right.
0 sin alpha cos alpha.
Right. Probably you are right. Probably you are right. You can check that today. I'll tell you how to do that. Anybody else? What's your name, by the way?
Vikramatilaka.
Vikramatilaka. Right. Anybody else who has tried?
So rotation around y-axis by an angle
Right.
beta.
Okay, what did you get?
Beta 0 minus sine beta, then 0 1 0 sine beta 0 cos beta.
Okay, probably all right too. Yes. Anybody else? All right. So, so let me open my MATLAB. I'll show you how to check that. Right. All right. So this is my MATLAB. By the way, how many of you have MATLAB installed in your laptops or your computers, desktops? No one? Right. How many of you have used MATLAB in the past? You can raise your hands. Right. So almost all of you have done it in the past. Do you know how to install MATLAB on your laptop? It takes about it's big, right? If you install the basic version, it's like about even it will go to about 20 GB. Full system is like 75 GB. But you can download it from GitHub and install. I'll send out some information for you to download and install it on your machines because it is important, right? Once you do that, you can open it, and this is MATLAB. And also, I will send out that information to you. There is a very nice robotics vision and control toolbox, RVC toolbox, written by Peter Cock in Australian National University, right? For a long time, it was a very famous robotics toolbox for MATLAB. But recently, MATLAB has got its own robotic systems toolbox. When you install, you can get that toolbox also, right? To do certain robotics operations, like for example, Vikramadilaka said you tried the rotation around x-axis by theta, right?
Alpha.
Yeah. So this is what you do. Say rotex. Let's say this angle is 30 degrees. So let's say pi by 6. So this is the rotation matrix. Rotex pi by 6, pi over 6, right? It's a 30 degree. Yeah.
I think the screen is not shared with us, sir. Still we can see the presentation slide.
All right. Can you see it now?
Yes, sir.
Right. But you heard everything I told, and this is the MATLAB. Once you open it, I will send out you information that you need to follow to download and install MATLAB. Once you install MATLAB, you have to also unpack robotics toolbox, and then from MATLAB you have to set path, right? Set path to robotics toolbox. There you can see the set path, right? Once you click it, this will open up. Then you can add with subfolders, this one, right? Any package, right? Any toolbox that you download, any third-party toolbox that you have downloaded, like robotics vision and control toolbox, you can just save it to any location on your hard drive and then figure that out. Then once you say okay, it will be added to this list. After that, you can actually launch these commands. Say rotex pi by 6 is a rotation around x-axis by 30 degrees. And if you say around x-axis minus 30 degrees, and this is the answer. Okay. And what about rotation around y-axis, right? 30 degrees. So like that. It's pretty easy. So you need to get your hands on MATLAB, right? And make your life easy. And what about this one? So if you look, all the matrices that we have done, 3 by 3, this is rotation matrix, rotation, right? So, but if I say T dot x, then you get the same answer, but now it is 4 by 4. Can you see that? Right. Hope you can see my screen. Can you see my screen, please?
Yeah.
All right. So the two things two MATLAB commands you need to know is trot and just rot, right? Rot x, rot y, rot z, right? Is an angle around x, y, or z, and the command generates the rotation matrix. And if you want to do want to have homogeneous transformation matrix, right? It is T rot T. All right. Okay, so you can try it out yourself and have some fun with MATLAB. So let me get back to the presentation. So this rotation is sometimes is described as an operator, right? So if you see over here, right, mathematically speaking, this is just an operator, right? It operates on a certain angle. Argument, this is operator, this is an argument. Okay, so you have tried the rotation around x-axis by theta, and this is the basic rotation matrix you get. Theta 30 degrees, and this is what you get. And this is what's happening in the real world. You have the coordinate frame, and there's a P1 vector like this, P1. And then P1 has undergone a rotation theta degrees, right? Positive. And now it is P2. Now, if you want to find out what is the new value, new vector P2, and this time the rotation is happening with regard to the vector. The vector rotates, not the coordinate frame. There's no other coordinate frame than what you see here, but the vector rotates. Right, earlier, what you saw was the vector attached to another coordinate frame, and the coordinate frame rotates. Either way, it's the same result. Okay, so you can look at this as an operator also. Now, if you put the translation only, if you look at the translation, which is the linear displacement, okay, so the operator, you can write it like this: AP2 is equal to AP1 plus AQ. So AP1 is the vector before the translation, AQ is the translation. So Q is the displacement, right? P1 is the original vector, this one, and you move it from here to here, and this is P2, right? The end point is over here. So what you want to do is you have to add this one to this one, right? Vector addition. So rotation is like in the previous case, right? And the translation is like this, just simple addition. So when you put them together, you can generate rotation part, which is a multiplication, and this is just an addition of 3 coordinates, and eventually you can write it like this. This actually only a linear translation. So if you look at ADQ, and what you see inside, it's just this, right? If you look at the rotation part, there's no rotation because it is a unit matrix, 1, 1, 1 along the diagonal and off diagonals zeros. So there's no rotation. But there is QX, QY, QZ, that is the linear translation from here to here, the coordinates of this point, right? So when you combine, when you generate the homogeneous transformation matrix, you can actually fill it using the rotation information here and the translation information here, totally independently. Okay. Now let's get back to the manipulator we looked at initially. Is a ironing mobile manipulator. You have a mobile platform, on top of that the robot, and it's doing some sort of ironing, right? So then if you look at the mathematics, how do you describe the mobile platform, the robot, the ironing board, everything, right? You are working with so many different coordinate frames like that. Frame A, right, frame B, frame C, frame D, like that. So you can write down the relationship between coordinate frames using the homogeneous transformation matrix, like ABT describe how B is oriented and translated with respect to A, how B has been rotated and then translated, right, with respect to A. So that information is here, ABT. And also you can say, for example, how B is rotated and translated with respect to, sorry, the other way around. You can also say how C is rotated or disoriented and translated with respect to B. And that is over there, BCT. So likewise, you can write down these coordinate transformation matrices, homogeneous transformation matrix, right? Between any 2 coordinate frames. And at a time, you are handling so many homogeneous transformation matrices. So when you have more than 2 coordinate frames, right, you have to write down the description of a coordinate frame going through other coordinate frames. Okay, if you want to go to Colombo, right, if there's a direct bus from wherever you are to Colombo, you can take that bus. Else you have to get it from one place to another place and get on another bus, like that. You have to go through several buses, right, until you get to the destination. Here also, if you want to write down, say, the homogeneous transformation matrix of C with respect to A. So essentially, what does that mean? How C is disoriented and translated with respect to A. If you want to find out that information, given ABT and BCT. So what are they? ABT means how B is disoriented and translated with respect to A. And what BCT is, and that is how C, frame C, is disoriented and translated with respect to B. Right? So if you know this one and that one, you can actually find out how C is disoriented and translated with respect to A. Pretty simple. So this is the process. First, you write down the equation that is a very familiar equation to you between A and B, right? Between A and B. So if there's any vector, right? If there's any vector attached to B, right? Like BP, for example, if you pre-multiply it with ABT, what you get is the description of that vector with respect to A. All right. So that is equation number 1. And at the same time, if there's a vector attached to C, right, and if you pre-multiply it with BCT, what you get is the vector described with respect to B. Okay, so that is between B and C. B and C. Now you can see this BP and this BP. So what you do is you replace this BP with this one, BCT times CP, and put it over here. Right? In place of BP, now you write CBT CP. Now if you look at very carefully what you have got here, it is AP here, CP here. AP here, CP here. So what is this operator here? What is this operator here? And you have already figured out this is CP, this is AP, and whatever it is, this should be the homogeneous transformation matrix of C with respect to A. Okay, C with respect to A, which is ACT. So ACT is equal to ABT BCT. So it's easy to remember because you can say this B and B cancel out. This is like chain rule in calculus. B and B cancel out. It is ACT. Understand? ACT is equal to ABT BCT. Chain rule. So with this mathematical tool, we can actually relate neighboring coordinate frames, and you have the chain rule so that you can have any number of coordinate frames in between, and you can actually relate a far distant coordinate frame like C to your first coordinate frame. Okay. Any questions, please? All right, so we move on. Please ask if you don't understand. So some graphics are missing here. I don't know why. I think it should be the same graphics here, right? Same graphics here. You can see APBORG. Right, anyway, so we can explain this pretty easily. So what is the contents inside ACT, right? ACT is the homogeneous transformation matrix of C with respect to A, right? So when you have these two coordinate homogeneous transformation matrices multiplying each other, right? So in the homogeneous transformation matrix like ACT, what you write, the top left 3 by 3 portion, right, is the rotation matrix. how C is oriented with respect to A, right? How C is oriented with respect to A. So that is over here, this part is the rotation of C with respect to A. So that is A, C, R. Okay, so that's over here. Now you saw the chain rule just a while ago. So if you want to have ACR, you can write it like ABR times BCR. Pretty easy, okay? ABR, BCR. So this is the upper left 3x3 partition of ACT. Now what is over here? So what is over here? This is the this is 3x1 vector. Okay, 3x1 vector of the position of C with respect to A. So I can write it. This is position of C, that is ORG, C ORG, origin of C with respect to A, So if you go back, this point, right, this point with respect to A, that is this vector, right? What is this vector? This is the position coordinate, position vector of C, origin of C, okay? Origin of C with respect to A. Origin of C with respect to A. What is this vector? Can anybody give me that answer? Can anybody give it a try? What is this vector? This vector is equal to this vector plus this vector, right? Vector addition. This vector is APBORG. This vector is BPCORG. But can you add them together? Yes or no? No, we cannot add them together. Then what should we do? What is the reason why we can't add them together? They belong to different coordinate frames.
Yes.
This one belongs to A. This one belongs to B. That is why this is called APBORG. And this is BPORG. So they belong to different coordinate frames, A and B. And eventually what we want is that this point with respect to A. So therefore this is okay. APBORG, this part anyway belongs to A or referred to A. So therefore you don't have to change it. But this one is not referred to A. So you have to change this description from B to A. How do you do that?
Multiply by
You multiply this by the rotation matrix of what? Of what?
ABR.
ABR. That's right. So that is rotation matrix of B with respect to A. Fine. So when you do that, you get this one. ABR, BPCORG added to APPORG. So this is just what I just explained, right? So that is the homogeneous transformation matrix. If you go through a via coordinate frame, so you are going from A to C via B. So in that case, homogeneous transformation matrix changes like this. Any questions up to that point? All right. So then when you have so many homogeneous transformation matrices, so many coordinate frames, right? When you do projects, this is the situation. Let's say you have a robot, you have the tool, you have other objects in the workspace. So everyone has a coordinate frame. There are cameras, right? You take the feed from the cameras. You need to know the location of the cameras, the orientation of the cameras. Otherwise, you can't interpret what you see, right, through the camera. So there are so many different coordinate frames. So in a situation like this, A, B, C, D, etc., right? So if you go a complete round, let's say ABT multiplied by BCT, then you get ACT, okay? How C is oriented with respect to A. But without stopping, if you continue with CDT, then B and B, C and C cancel out, you get ADT. So that is how D is oriented with respect to A. And if you further go DAT, what will happen? B and B cancel out, C and C cancel out, D and D cancel out. It is A to A homogeneous transformation matrix. So A to A homogeneous transformation matrix is how A is disoriented and translated with respect to A itself. So there's no disorientation and there is no translation of A with respect to A itself. So therefore, the answer should be 1 or identity matrix. Okay. So this is this equation you can use and adjust it in various ways. Like if you want to find out BAT, right? BAT. What is BAT? BAT is ABT inverse. ABT inverse. So if you multiply this with ABT, right? If you multiply this with BAT, so this side BAT, oops. So if you multiply this side with B A T and also this side BAT, both sides, right? What happens is that this BAT and this ABT cancel out because ABT is the inverse of BAT. So when you multiply a vector, a matrix with its inverse, the answer is 1 or identity. So that goes out. What is remaining is only this part. BCT, CDT, DAT. Like over here. Right? So this compound equations of homogeneous transformation matrices, right? You can write what you know, and then you can try to adjust it by pre-multiplying or post-multiplying by other matrices to find something that you do not know. Okay. All right. Yeah, that's it for that lecture. Any questions so far? Right. So